Today we're going to be looking at the principal operations of hardware devices. So this part of the unit is a bit of recap of IGCSE, and we're not going to look at all kinds of hardware out there. We're going to be looking at specific devices. So you're going to be focusing on input and output devices, in particular laser printers, 3D printers, microphones, speakers, touchscreens, and virtual reality headset. That doesn't exclude the need to know all the other types of devices like keyboards and mice. However, chances are that the kind of questions you're going to be getting are going to be focused on input and output devices that are shown on screen. So let's begin by looking at some key terms. Do pause the video and jot these down. You should know the difference between binder 3D printing, which is a method of 3D printing that uses two stages. The first stage is use a dry powder, and the second stage uses a binding agent, which is kind of like a glue that fixes that dry powder. Then you go direct 3D printing, where the print head moves in X, Y, and Z direction, and you have layers of melted material, normally PLA plastic, which are deposited on a bed, and it kind of works like an inkjet printer really. You should also know digital to analog converter and analog to digital converters. This is the same as IGCSE. Organic LEDs, OLED, you need to understand how they work. And then obviously screen resolution, which is the number of pixels in horizontal and vertical directions on a computer screen or a TV or your mobile phone, for example. In particular, pay attention to OLED because that is something new. Then there's touchscreens, which you're familiar with, which can come in capacitive or resistive flavors. So capacitive, where you touch the screen and you change an electrical field. And obviously they have problems that, when you wear gloves, they don't work. And then you got resistive, where it uses a kind of pressure, where the top glass layer touches the plastic layer, and that completes the circuit. And then of course there's virtual reality headsets, which are fairly new for this year. We did not cover them at IGCSE. And then our good old friend, the sensor. Now let's begin by looking at printers in particular. So printers come in all kinds of flavors: lasers, inkjets, and obviously 3D printers. Laser printers use dry powder ink rather than liquid ink, and they make use of the properties of static electricity to produce text and images. So they basically print the whole page in one go rather than kind of line by line. And laser printers normally use 4 toner cartridges instead of liquid ink, and these are blue, cyan, magenta, and black. One of the most important things you need to remember though is the sequence. What happens when you press print? So here you'll be looking at stage 1, where data from the document is sent to the printer driver. The printer driver ensures that data is in the correct format for the chosen printer, and then it follows the steps. So do pause the video and go through these stages. You will probably be asked to write these stages down or put them in some kind of order in an exam. Next up is inkjet printers. Same kind of thing again. The stages are on the right hand side. You need to be aware of those stages. They're pretty much similar to laser printer, but somewhere down the middle the printing process differs. So just be aware of what the difference between the way inkjet printers print and laser printers print, what the differences are. So inkjet printers in particular use a printhead, which consists of nozzles that spray droplets of ink onto the paper to form characters. Instead of using a toner, they use ink cartridges. So you'll end up with blue, yellow, and magenta, and often a black cartridge. Sometimes you end up with a single cartridge that contains all the colors and black. There's a stepper motor involved and a belt which moves the print head, which goes across from page to side by side. So it's kind of like line by line. And there's a paper feed which automatically feeds the printer with pages that they require. Now, if you've got access to an inkjet printer, you can just open it up and you can see how the paper feed works and how the stepper motor moves the print head. That's very easy to see. So when you try to change the cartridges, you will see it move from left to right as a test. Now, inkjet printers come in 2 flavors. The first one is thermal bubble, and the other one is piezoelectric. Now the thermal bubble basically contains tiny resistors which localize heat. They create the heat, and this makes the ink vaporize. A tiny bubble which is formed when the heat is generated, and as it expands, some of the ink is ejected from the printhead onto the paper. When the bubble collapses, a small vacuum is created which allows fresh ink to be drawn into the printhead, and this continues until the cycle is completed. The piezoelectric one uses a crystal which is located at the back of the ink reservoir for each nozzle, and the crystal is then given an electric charge which makes it vibrate, and the vibration forces the ink to be ejected onto the paper. When that happens, more ink is drawn into for further printing, and the process keeps on repeating. So they both use different types of technologies, but they have the same type of operation. Now 3D printers are used to produce working solid objects, whether it's medicine, whether it's construction, whether it is just prototyping products. You can do a lot with 3D printers, and they're becoming more and more advanced, especially in the kind of materials they use. Now there's a lot of different types of materials possible. There's powdered resin, there's powdered metal, paper or ceramic, and there's a lot of different types of 3D printers. So they can vary from the size of a microwave oven to the size of a small car, or even in some cases size of houses. Now 3D printers use additive manufacturing. The object is built up layer by layer, and this is in contrast to the more traditional method of subtractive manufacturing, where you remove material. So think of a sculpture being made out of stone. You're removing material to create that sculpture. That's subtractive. Whereas when we add things up, build it layer by layer, that is additive manufacturing. Now direct 3D printing uses inkjet technology. Same like your inkjet printer, a print head can move left to right as a normal printer would. However, the print head can also move up and down to build up the layers of an object, so it moves in X, Y and Z directions. Another type of 3D printing technology, it uses binder 3D printing, which is similar to direct 3D printing. So it still uses the same process, but it takes two passes. The first pass deposits a dry powder, and that's layered, and the second pass delivers a binding agent, which is kind of like a glue, and that spray to kind of form the solid layer. So you spray the dry powder, then you spray the binding agent, and then you keep repeating the process. Now newer technologies use lasers and UV light to harden liquid polymers, and this further increases the diversity of products which can be made, especially when you're looking at biomaterials and construction. So do pause the video or rewind it and make sure that you understand inkjet, laser and 3D printing really well. We're now going to move on to speakers, and chances are you already know a bit about speakers and headphones. So speakers basically use digitized sound which is stored on a file or a computer, and that can be converted into sound. And normally what happens is that on a computer, sound data is normally stored in ones and zeros. This digital data is first passed through a digital to analog converter, where it's converted into an electrical current. This then passes to an amplifier, since the current generated by the DAC will be very small, and that then creates a current large enough to drive a loudspeaker or a headphone. This electric current is then fed to that loudspeaker, where it's converted into sound. So the diagram that you see on screen kind of illustrates the process, how digital data can be converted into analog waves and then amplified so a loudspeaker can reproduce it. Now the rate at which the digital to analog converter can translate the digital output into analog voltages is known as the sampling rate. You need to go a bit more deeper than that. So you will need to understand how the speaker actually uses electric current to create sound. So basically what happens is, when an electric current flows through the coil of the wire that is wrapped around an iron core, the core becomes a temporary electromagnet. So a permanent magnet is positioned very close to this electromagnet, and as the electric current passes through the coil, the induced magnetic field in the iron core changes, and this causes the iron core to be attracted towards the permanent magnet, and as the current varies, this causes the iron core to vibrate because it's moving backwards forwards. And as the iron core is attached to a cone, which is normally made out of paper or a thin synthetic material, this causes the cone to vibrate, which then produces the sound. So do pause the video and have a look at the diagram to identify the different parts. You should be able to explain how the speaker part works. Now hopefully microphones are also familiar to you from IGCSE, and a microphone normally converts sound waves into an electric current, so they work on the opposite side. So when a sound is created, for example, I'm speaking right now, it's causing the air to vibrate, and this vibration is being picked up by the diaphragm in the microphone, which then begins to vibrate. So there is a copper coil wrapped around, again, a permanent magnet, and the coil is connected to the diaphragm. As the diaphragm vibrates, the cone moves in and out, causing the copper coil to move backwards and forwards. And this motion again causes a magnetic field around a permanent magnet to be disturbed, which induces an electric current. And this electric current is then either amplified or sent to a recording device. And the electric current is analog in nature. Now, once this electric current is output from the microphone, it's sent to a computer where a sound card normally converts the current into a digital signal, which then can be stored in the computer. So the sound card probably will be using an analog to digital conversion process. On screen, you see an example of a sound wave for the word hut and the digital value after conversion. So the word has been picked up by the microphone and is converted using an ADC into digital values, which can then be stored in the computer or manipulated as required using appropriate software. So do rewind the video. Make sure you know how both microphones and speakers work and how especially the electric current, the role of the coil, the role of the iron core, the diaphragm or the cone, and the magnet, how all of that comes into play. Next up, we're going to be looking at screens, and you use screens all over the place, from your smartwatch to your television to your mobile phone, and screens are normally used to show the output from a computer. Modern screens use an LCD, often backlit with LEDs or newer organic light emitting diodes, and these screen displays are based on the pixel, which is the smallest picture element concept, where each screen pixel is made out of 3 other subpixels, which are red, green and blue. By varying the intensity of the 3 subpixels, it's possible to generate millions of colors. The greater the number of pixels on screen, the greater the screen resolution. The number of pixels which you can probably view horizontally and vertically on a screen. For example, 1680 by 1080 or 1920 by 1080, which is full HD. Now, LCD and OLED screens use this type of pixel matrix to make up the picture as well. Whether it's LCDs, whether it's LEDs, whether it's OLED, you're working with pixels and you're using multiple subpixels to generate colors. The difference between LCD is that LCDs require normally a light source, whereas LEDs and OLEDs are backlit, so you do not require a light source to illuminate these pixels. Now, we're going to only be focusing on OLED because that's the key technology. However, you need to know the difference between OLED and LCDs and LEDs as well. OLEDs use organic material, which is normally material made out of carbon compounds, and these allow us to create flexible semiconductors. Now, organic films are sandwiched between 2 charged electrodes, a metallic cathode and other is a glass anode. So when the electrical field is applied to the electrodes, they will give off light. Now, this means that there's no form of backlighting required. This allows for very thin screens. It also means that there is no longer a need to use LCD technology, since OLED is a self-contained system itself. So do pause the video and just have a look at the diagram to identify the different layers. The benefit of OLED is that we're now getting bendy smartphones, which are pretty flexible, so you can bend these devices. You can get curved screens, which are much more suitable to various purposes, rather than having fixed rectangular thick LCD screens. Now, talking about LCD screens, let's look at LCD touch screens. Now, these LCD touch screens can be capacitive or resistive. So capacitive basically means you make them up of many layers of glass that act like a capacitor, and they end up creating electrical fields between these glass plates. So when the top glass layer is touched, the electric current changes and the coordinates where the screen was touched are determined by an onboard microprocessor. The benefits of this type of technology is that it's medium cost, so it's not very cheap, but it's not very expensive either. The screen visibility is good because you're using LCD technology, especially in strong sunlight, because you've got a bit of backlight going on. It permits multiple touch capability, and the screen is very durable. It takes a major impact to break the glass. The drawback, on the other hand, is that it only allows the use of bare fingers as form of input. Any gloves, anything that insulates, makes the capacitive LCD touchscreen inoperable. Now, resistive LCD touchscreens are alternatives to capacitive ones, and these make use of an upper layer of polyester, which is normally a form of plastic, and the bottom layer of glass. So when the top polyester layer is touched, the top layer and the bottom layer complete a circuit, and signals are then sent out, which are then interpreted by a microprocessor, and the calculations determine the coordinates of where the screen was touched. Now, the benefit of this is that it's relatively inexpensive and cheap technology. It's possible to use bare fingers, gloved fingers, stylus, because you're not relying on conduction, you're just simply relying on pressure. The drawbacks, on the other hand, are that the screen visibility is very poor, especially in strong sunlight. It does not permit multi-touch, and the screen durability is only fair. It is vulnerable to scratches, and the screen wears out through time because you've got that top polyester layer. Make sure you understand the different types of touch screens and the difference between OLED and LCD. LCD requires backlighting, older technology, thicker screens. OLED is more flexible, using carbon compounds, and can lead to thinner screens. Now, next we're going to be looking at virtual headsets, and you must be familiar with virtual reality. Most of the time we use virtual reality for entertainment. However, virtual headsets are also used in situations which are dangerous for humans. The process normally works like this. Video is sent from a computer to the headset, either using an HDMI cable, or you normally have a fitted smartphone that fits inside the virtual headset itself. Two feeds are sent to an LCD or OLED display. Sometimes two screens are used, one for the left side of the image and one for the right side of the image. Lenses are placed between the eyes and the screen that allow for focusing and reshaping of the image, kind of give that 3D effect. And most headsets end up using a 110 degree field of view, which is enough to give a pseudo 360 degrees surround image or video. Frame rates play a huge part in the experience. So if you have a frame rate of 60 to 120 images per second, you're going to have a much more smoother 3D effect. And what also happens is that normally these headsets have a series of sensors or LEDs with a camera which allow the image to react to the head movement. The sensors normally are gyroscopic or accelerometers, which are normally built into most phones. The headsets also use surround sound, binaural audio, and some headsets also use infrared sensors to monitor eye movement in addition to your head movement, which allows the depth of field on the screen to be a bit more realistic. Now, these type of headsets come in all sorts of different varieties. You can have the very expensive two-screen built-in, powered by a computer, uses either an HDMI cable, or modern ones uses wireless technology as well, or you can have the cheap ones which are basic plastic headsets where you have to fit your own smartphone and they use the smartphone technology to power them. Now, if you really wanted to kind of see how the world looks, just try to close one eye. So put a finger in front of your face and close one eye and look at the position of that finger. Then open the other eye and close the first one. So you will see that your finger is moving, and that basically is how virtual reality headsets work. So they try to fool your eye into thinking by kind of projecting an image which is in two different places. So when you're looking at it from both eyes, you create this 3D stereoscopic 360 degree world. Now, sensors are obviously used in virtual reality headsets as well. So let's start looking at sensors in a bit more depth. Again, you might be familiar with a lot of these. Sensors are input devices which read or measure physical properties such as temperature, pressure, acidity, and so on. And the data they generate is analog in nature. This means it's constantly changing and does not have a discrete value. Analog data usually requires some form of interpretation, and computers cannot make any sense of these physical qualities, so it needs to be converted into a digital format. And this is usually achieved by an analog to digital converter, kind of like how sound operates. Just remember that sensors do not do any kind of processing. They simply measure. So sensors' job is to just measure what's going on in the real world and pass it on to the ADC or the computer. The computer or the device or the microprocessor makes sense of the data and makes decisions based on it. So some of the common sensors are on screen. See if you can identify what they are. So temperature, moisture, light, infrared, pressure, acoustic or sound, gas, pH, magnetic fields. There's some example applications also given for each type of sensor, so do pause the video and go through these. And when you're ready, let's continue. Now, sensors are used in monitoring and control systems. So what's the difference between both of these? Well, monitoring systems simply monitor the environment. They normally use a sensor which detects what's going on in the real world and then passes it on to a microprocessor. The microprocessor will probably compare it to some preset values, and then it will either raise an alert or do nothing. A control system, on the other hand, will use a sensor. It will monitor the environment, and based on the data that's read by the sensor, the microprocessor will compare it to a preset value and then tell an actuator to influence the environment. So an example would be that you got a temperature sensor in an air conditioner. The temperature sensor will measure a temperature and say the temperature reaches 28 degrees. So it sends that data to the microprocessor. The microprocessor will compare it to a preset value of 25 degrees, that okay, it's too hot if it's over 25 degrees. So once it detects it, that temperature is a bit higher than 25 degrees, it will send a signal to an actuator, which probably controls the cooling unit, which will start throwing cool air into the room. Now what happens is that the environment cools down, the temperature sensor now detects the new temperature, which has now probably gone down to 24 degrees. It then sends this data to the microprocessor, probably using an ADC. The microprocessor then does another comparison and says, well, okay, the temperature is now too cold. It will then send a signal to the actuator to turn the cooling unit off. And that's basically a control system which uses output to influence the input. So it's got a feedback loop going on. Now on screen you can see some examples of monitoring system and control system, and also a flow chart that explains how they differ from each other. We also talked about actuators, which are a form of an output device. So let's look at that in a bit more depth. So when a computer is used to control devices, normally a motor or a valve, something like that, is used, and digital data needs to be sent in analog forms to control these devices. Now, an actuator is an electromechanical device such as a relay or a solenoid or motor, and these actuators may require a digital to analog conversion process, so they end up receiving an electric current rather than the digital signal, which is ones and zeros. But sometimes you can have a solenoid which can be a digital actuator, and in that case you don't require a DAC. So think about what's happening in a loudspeaker. That kind of works around the same principle. You take some digital bits and then you convert them to an electric current, which then creates a vibration and then sound is generated. Now actuators are very commonly used in control applications. They are technically output devices. However, they are mentioned here because they are an integral part of a control system. It's not possible to have a control system without some form of actuator. They will probably end up as monitoring systems otherwise. Now, we just mentioned briefly what positive feedback was. So positive feedback is that you take the output from the system, which then affects the next input. So the cycle continues on. So the sensor readings may cause the microprocessor to alter a valve or a motor, or they will trigger the cooling unit, which will then change the next reading taken by the sensor. So the output from the microprocessor will impact the next input. This is what is meant by positive feedback. Now your task is to investigate the use of sensors and actuators. You can draw a diagram of a sensors, microprocessors, ADCs, DACs, actuators work together, and on screen you've got 7 different possible scenarios. Anti-lock braking systems, greenhouse systems, street light systems, traffic monitoring systems, automatic doors, home lighting systems, lift systems. I would recommend that you find out about all of them and then maybe pick one, the one that you perhaps find the most complex, like an anti-lock braking system, and then create the diagram for just that one. Okay, so don't go for something like a street light system or automatic doors or a lift system. They're pretty simple. So you might want to just focus on anti-lock braking system, because that seems to be the most complex of them all. Okay, a lot of different types of sensors all influence how the braking system works. Okay, so by now, hopefully, you can explain the process of laser printing and inkjet printing, give benefits and drawbacks for capacitive and resistive touchscreens, be able to explain how speakers work, how microphones work, how virtual headsets work, and how sensors and actuators work together in control systems, and how monitoring systems work. That's all from me for today. I'll catch you in the next lesson.